Curve sketching. In this section, we will explore more about curve sketching. We have learned how to find vertical and horizontal asymptotes in the past. The line x equals c is a vertical asymptote if either limit x approaches to c from the left of your function gives you positive or negative infinity, or you could also send x to c from the right of your function gives you positive or negative infinity, then you do have vertical asymptote, and vertical asymptote is a vertical line. So equation is x equal number, and it will be the number that x was trying to reach. Horizontal asymptote can be found when you send x to infinity or x to negative infinity. Limit x approaches to positive infinity of your function gives you a real number L, or limit x approaches to negative infinity of your function gives you a real number L, then you do have a horizontal asymptote y equal that L. It's that limit that you get. We also learned that because your function could behave differently as x approaches to infinity or x approaches to negative infinity, you could have at most two horizontal asymptotes, and vertical asymptote could occur at any x. And there is no limit on how many vertical asymptotes a function could have. For example, as you all know, a tangent function has infinitely many vertical asymptotes. There is an asymptote that we have not go over yet, and that would be slant asymptote. Slant asymptote occurs in a rational function when both of the following conditions occur. So first condition is degree of the numerator is exactly 1 higher than the degree of the denominator. So look at the example below. I got f of x equal quantity 2x squared plus 10x plus 15 over quantity x plus 3. You can see that degree of the numerator is exactly 1 degree higher than degree of the denominator. So it is possible that this function could have slant asymptote. And this is not enough a condition to determine yet whether this function has slant asymptote or not. When you do the long division on this function, you got to have remainder in order for this function to have a slant asymptote. Think about it. For example, let's say I divide this function 2x squared plus 10x plus 15 by x plus 3. Let's say it perfectly divides as a 2x plus 5 and there was no remainder. That means this function could be factored as x plus 3 and quotient 2x plus 5 without any remainder. Then this would have been canceled. So this function is just aligned with the whole at x equal negative 3. So it will not have any slant asymptote since the graph is just aligned with a hole in it. So in order for a rational function to have slant asymptote, degree of the numerator is exactly 1 degree higher than degree of the denominator, and there has to be a remainder when you perform the long division. Let's do an example. Determine all the asymptotes for f of x equal quantity 2x squared plus 10x plus 15 over quantity x plus 3. So let's first find the vertical asymptote. And because I have a denominator x plus 3, this function is undefined when x equal negative 3. So we can find the limit x approaches to negative 3 either from the right or left. It doesn't matter. So I'm going to just go from the right of quantity 2x squared plus 10x plus 15 over x plus 3. Let's do the direct substitution now. So I have 2 times negative 3 squared plus 10 times negative 3 plus 15 over, as x approaches to negative 3 from the right, here's a -3, here's a -2, here's a -4. So -3 from the right is -2.9999999 plus 3 gives you 0.000000001. So that will be a number getting close to 0 that is a positive number. And my numerator, when you calculate, I get -3 squared is 9, 9 times 2 is 18, minus 10 times -3 is -30, plus 15 over a positive small number. And because you get +3 over a positive small number, you do get positive infinity. So yes, you do have a vertical asymptote, and your vertical asymptote equation is x equal number, and the number is -3. Now, let's see if we have a horizontal asymptote. Horizontal asymptote occurs when degree of numerator is less than or equal to the degree of the denominator. But my degree of the numerator is higher than the degree of the denominator. So you don't have a horizontal asymptote. Now, how about slant asymptote? Well, degree of numerator is 2, degree of denominator is 1. So it is possible, but I better have a remainder when I perform the long division. So let's go ahead and divide. I'm going to divide 2x squared plus 10x plus 15 by x plus 3. X goes to 2x squared, 2x times, multiply, multiply. So when you multiply x times 2x, you get 2x squared. 3 times 2x is positive 6x. Now you are going to subtract top polynomial minus the bottom polynomial. And you recall when you subtract polynomials, 2x squared plus 10x plus 15 polynomial, subtract the bottom polynomial. And what happens? Yes, you have to distribute the negative to the second polynomial, which will resulting in changing their signs to opposite. So you can just change their signs to opposite, and go ahead and add the top to bottom. So 2x squared is gone. 10x minus 6x now, which is 4x plus 15. My divisor still have the same degree than my remainder, so I can divide one more time. So divide one more time. X times what is 4x? That will be positive 4. So now multiply, multiply. X times 4 is 4x. 3 times 4 is positive 12. Again, you're gonna subtract top polynomial minus the bottom polynomial, which will change the bottom polynomial's signs to opposite. So positive 4x become negative 4x, positive 12 become negative 12. Now you can just add. So 4x minus 4x becomes 0. 15 minus 12 is 3. So you do have a remainder, which means you have a slant asymptote. And what is the equation of slant asymptote? It is y equal the quotient of your long division. So you had to do the long division anyway, because as you do, you can find out whether you have slant asymptote or not. And then once you do, then your answer is y equal this quotient. And that's your slant asymptote. So condition for horizontal asymptote is degree of numerator less than or equal to the degree of denominator. And condition for slant asymptote is degree of numerator being greater than degree of denominator by exactly 1 degree. So these two cannot happen at the same time. You notice that above example 2, I have a slant asymptote and I do not have a horizontal asymptote. So do not waste the time looking for both of them. because it will never happen. Determine all the asymptotes for f of x equal quantity 2x squared plus 11x plus 15 over quantity x plus 3. You notice that this numerator factors, and it factors as quantity 2x plus 5 times quantity x plus 3 over quantity x plus 3. So to find the vertical asymptote, we take the limit as x approaches to the number that makes this function undefined, which is negative 3. Let's go from the right. Of this function, I'm gonna use the factored form, which is quantity 2x plus 5 times quantity x plus 3 over quantity x plus 3. And as x plus 3's get canceled, the limit would be 2 times negative 3 plus 5, which is negative 1. And because limit is not positive infinity or negative infinity, this tells me there is no vertical asymptote. Secondly, how about horizontal asymptote? Well, horizontal asymptote occurs when degree of numerator is less than or equal to the degree of denominator. But my degree of numerator is larger, not less, than the degree of denominator. That means there is no horizontal asymptote either. Lastly, let's hoping for slant asymptote as degree of numerator is exactly 1 degree higher than degree of denominator. So as you do the long division, 2x squared plus 11x plus 15 divided by x plus 3. X goes to x squared, 2x times, multiply, I get 2x squared, multiply, I get positive 6x, subtract top to bottom. I'm going to change the bottom polynomials to opposite signs. This is gone. 11x minus 6x is 5x now. Putting down the 15. And x goes to 5x plus 5 times. X times 5 is 5x. 3 times 5 is positive 15. Subtract. Again, when you switch bottom polynomials assigned to opposites, 5x minus 5x is 0. 15 minus 15 is 0. So I don't get any remainder. Therefore, there is no slant asymptote either. So this problem looked really similar to one we just did. However, earlier we had slant asymptote and we had a vertical asymptote. This problem has no asymptotes, period. In fact, as you can tell from the beginning, as this guy factors, this function is just a line y equal 2x plus 5 with a hole at x equal negative 3. So there will be no asymptotes at all on this graph. Next example. Determine all the asymptotes for f of x equal 12x over square root of quantity 4x squared plus 3. So first of all, for vertical asymptote, let's look at our denominator. I have square root of quantity 4x squared plus 3. Quantity 4x squared plus 3 is always greater than equal to 3, which means it's never 0 because it is greater than equal to 3. Therefore, there will be no vertical asymptote. Next, how about horizontal asymptote? Would there be any horizontal asymptotes? What is the degree of my numerator? Yes, it is 1. And square root of 4x squared, that's the highest power of your denominator, and that would be either 2x or negative 2x, since square root of x squared is the absolute value of x. Whether it comes out as a x or negative x, degree is still 1. And because degree of numerator is less than or equal to the degree of denominator, you will have horizontal asymptotes here. In fact, because your rational function has a square root in it, you will have two horizontal asymptotes as you previously learned. So let's get them. First one is limit as x approaches to positive infinity of your rational function, 12x over square root of quantity 4x squared plus 3. And because if you are to substitute infinity for x right now, you will get infinity over infinity as their degrees are the same. So in this case, we had to multiply by quantity 1, which is a quotient of 1 over highest power of your variable in the denominator. And in the denominator, highest power is square root of x squared, which is an absolute value of an x. But because x is approaching to positive infinity at the moment, x is a positive number, so this will be equal to just x. So on the numerator, I can use 1 over x since there is no radical in the numerator. But because denominator has a radical, we will leave it as 1 over square root of x squared. So then this is equal to limit x approaches to positive infinity. You multiply numerator with the numerator, but x's get canceled. So you get 12 on the numerator. And in the denominator, you're going to multiply radical times 1 over radical, which is same as 1 radical of quantity 4x squared plus 3 over x squared. But let's split the fraction. So 4x squared over x squared gives you 4 plus 3 over x squared is 3 over x squared. But limit x approaches to infinity of 12 on the numerator stays 12. And in the denominator, as x approaches to infinity, this value 3 over x squared approaches to 0. Therefore, all you're going to get is a square root of 4, which is 12 over 2, which is 6. So you get a horizontal asymptote y equals 6. Similarly, limit x approaches to negative infinity this time of this same function, 12x over square root of quantity 4x squared plus 3, multiply by quantity 1. But this time, square root of x squared is the absolute value of x. And at the moment, x is approaching to negative infinity, which means x is a negative number. So it's going to come out as opposite of x. So on the numerator, my 1 over radical x squared is actually negative 1 over x. And in the denominator, I'm still going to have 1 over radical x squared. Then this is equal to limit x approaches to negative infinity. X's get canceled again. I get negative 12 on the numerator. Square root of 4x squared over x squared is square root of 4 plus 3 over x squared. And x goes to negative infinity. This value goes to 0 again. And I'm going to get negative 12 over square root of 4 as my limit, which is equal to negative 12 over 2. Which is negative 6. So again, I get another horizontal asymptote, which is y equal negative 6. So like we said, we get two horizontal asymptotes, y equals 6 and y equal negative 6. How about slant asymptote? Well, we just learned today that horizontal asymptote and slant asymptote cannot happen at the same time. They are mutually exclusive cases. So if you have a horizontal asymptote, that means you cannot have a slant asymptote. Therefore, no slant asymptotes. Now that we know how to find all asymptotes, let's go ahead and do the curve sketching. And here is guidelines for graphing. First of all, when you are given a function, determine the domain of this function so that you know what are all the allowed values for x that can be used in your graph. Number 2, find all the intercepts. Find the x-intercepts by setting y equals 0, and find the y-intercept by setting x equals 0. Third, find all vertical, horizontal, or slant asymptotes as we just learned. Number 4, identify any extrema by finding critical numbers. You can do the first derivative test and find the relative extremas. Lastly, identify any points of inflection so that you can use which interval you should graph concave up or concave down, and also verify where the concavity changes. Now let's go ahead and start the actual curve sketching example. Use the guidelines for graphing to sketch the graph of f of x equal quantity x squared minus 2x plus 4 over quantity x minus 2. So first step was to find the domain. What is the domain of a rational function? Every time you have a rational function, domain is all real numbers except x such that the rational expression is undefined. And rational expression is undefined when denominator is 0. So domain will be all real numbers except 2 in this case, since this expression will be undefined when denominator is equal to 0. So we know x cannot be 2. So therefore, domain is negative infinity to 2 union 2 to infinity, and of course 2 is not included. Let's find the intercepts now. We can find the x-intercept by setting y equals 0, and we can find the y-intercept by setting x equals 0. I'm gonna find the y-intercept first since it's very simple. So to find the y-intercept, we set x equals 0, and that will be f of 0, because you are gonna plug 0 for every x you see, and that will be quantity 0 squared minus 2 times 0 plus 4 over 0 minus 2, which is equal to, that's 0, that's 0. I have a 4 over negative 2, which is negative 2. And your y-intercept is 0, comma, negative 2 then. Let's find the x-intercept now. Your x-intercept, we set y equals 0. And y is the f of x. So we set 0 on the left. And I have quantity x squared minus 2x plus 4 over x minus 2. And this rational expression is 0 when numerator is 0. And I don't think my numerator factors. So you can use quadratic formula, and that was x equal negative b. So that's the opposite of b, and my b is negative 2. So opposite of that is positive 2 plus or minus square root of b squared, and my b is again negative 2 square minus 4. A is 1, c is 4. 4ac all over 2 times a, and my a is 1. And if you look inside of square root, I have a 4 minus 16, which is not a real number. I get square root of negative 12. That means I do not have x-intercept. So I have no x-intercept. Third step, let's find all asymptotes. Do I have a vertical asymptotes? I think so, because there is an x such that it makes this rational expression undefined and your numerator does not factor. So let's do limit x approaches to, what is the x that makes the denominator undefined? That was 2. You can do either from the right or from the left. So I'm gonna do from the right. Quantity x squared minus 2x plus 4 over quantity x minus 2. And that will go to 2 squared minus 2 times 2 plus 4 over 2 from the right. You can think of 2.000000001 minus 2, which is positive very small number. And I get 4 minus 4 plus 4 on the top. I get 4 over positive very small number, which goes to positive infinity. So you have a vertical asymptote, and it is x equal 2. So my vertical asymptote is x equal 2. How about horizontal asymptote? Horizontal asymptote occurs when degree of numerator is less than or equal to the degree of denominator. And my degree of numerator is greater than degree of the denominator right now. So no horizontal asymptote. How about slant asymptote? Slant asymptote occurs when degree of numerator is exactly 1 degree higher than degree of the denominator. Is it? Yes, it is. Degree of numerator is 2. Degree of denominator is 1. So degree of numerator is exactly 1 degree higher than the degree of the denominator. So that's satisfied. And there was one more condition. And that was if we were to do the long division, we had to have a remainder. So let's perform the long division. I have x squared minus 2x plus 4 divided by x minus 2. X goes to x squared, x many times, x times x squared, negative 2 times x is negative 2x. Subtract top to bottom. I need to change the bottom polynomial to their opposite sign. So positive x squared become negative x squared. Negative 2x become positive 2x. So x squared minus x squared gone. Negative 2x plus 2x gone. And I get 4 as a remainder. So yes, since I have a remainder, this function has a slant asymptote, and your slant asymptote is y equal the quotient, and my quotient is x. So you found the slant asymptote. Next step, let's find all extrema. To find the extrema, we have to find the critical numbers. Critical numbers are x such that f prime is 0, or f prime is undefined, but f is defined. So let's first find the f prime. Since numerator and denominator is both pretty simple, I'm going to use quotient rule. Alright, so f prime of x is equal to low quantity x minus 2 times d high. Take the derivative of high, I get quantity 2x minus 2 minus high. And my high is quantity x squared minus 2x plus 4 d low. Take the derivative of low, which is 1 over square below. So square the quantity x minus 2. So let's go ahead and FOIL and distribute the negative on the second term, and we will simplify it. FOIL. X times 2x is 2x squared. X times negative 2 is negative 2x. Inner 2. Negative 2 times 2x is negative 4x. Last and last is negative 2 times negative 2, which is positive 4. Go ahead and distribute all the negatives to your second polynomial. I get negative x squared plus 2x minus 4 over quantity x minus 2 squared, which is equal to, let's simplify by combining like terms. 2x squared minus x squared gives you x squared. Negative 2x plus 2x is 0, but you still have minus 4x. And a positive 4 and a negative 4 disappear. So it is just the quantity x squared minus 4x over quantity x minus 2 squared. And your numerator factors as x times quantity x minus 4 over quantity x minus 2 squared. So when is this f prime ever 0? My f prime is 0 when numerator is 0 and denominator is not 0. And my numerator is 0 when x equals 0 or x is equal 4. So this is my critical numbers. How about, is this f prime ever undefined for some x, but it is defined for f? My f prime is undefined if x was 2, but if you go back to the original function, f is also undefined at 2. So that 2 is not a critical number. So be careful. In order for x to be a critical number, on the case where f prime does not exist, then that x has to be in the domain. If x is not in the domain, that means that x not even on the graph of your function. So it cannot be critical number where your relative max or relative min happens. So we found the critical numbers. So to find the relative max, relative min, we're going to locate our critical numbers on the f prime line. So when does my f prime does not exist? My f prime does not exist when x is equal to. However, this is not a critical number because 2 was never in the domain. If there is a number that's not in the domain, you should still include though in your sign graphs, because that's where your graph cuts off by vertical asymptotes or hole. So graph could behave differently before and after the point of discontinuity. I'm going to locate now the critical numbers at the point of discontinuity. So my critical number, one of them was 0. This is a critical number. And my f prime is undefined at 2. And actually there is a vertical asymptote there. And 4 is also a critical number. So that gives me 1, 2, 3, 4 intervals that I need to pick a test number from. My test point for fourth interval, I'm gonna choose -2. For second interval, it's between 0 and 2, so I'm gonna choose +1. And I'm gonna choose 3. And then after 4, I'm gonna choose 5. And of course, I'm going to plug it into factored form of f prime to find out the sign. So first test point, I'm gonna plug -2 to every x I see on my f prime. Then you get -2. -2 minus 4 is also negative quantity. -2 minus 2 squared is positive. So this whole thing become positive. So it is positive on the fourth interval. Let's test the second interval. Our test point is 1. 1 is positive quantity. 1 minus 4 is negative quantity. 1 minus 2 quantity square is positive. So this whole quotient is negative. So that's what you get on your second interval. Third interval, my test point is 3. 3 is positive quantity. 3 minus 4 is negative. Quantity 3 minus 2 squared is positive. So this whole quotient is negative. So third interval had no sign changes. All right, let's test the last test point, which is 5. 5 is a positive number. Quantity 5 minus 4 is a positive number. And quantity 5 minus 2 squared is a positive number. So this whole quotient is positive. So I get positive. So your graph is increasing and then decreasing. So at your critical number 0, you do have relative maximum here. Your graph has a vertical asymptote at 2, and then your graph is going down, and then it goes up from 4. So since there's a sign changes from negative to positive, so you do have relative min at x equal 4. So let's find them by plugging into original function. My relative max is 0, comma, f of 0, and f of 0, we already found it. Remember, that's your y-intercept. This function, when x equals 0, y was 2. So I know my relative max is 0, comma, negative 2. And what is the relative min? Relative mean occurs when x equals 4, and it will be f of 4, and f of 4 is equal to 4 squared minus 2 times 4 plus 4 all over 4 minus 2, which is equal to, I have a 16 minus 8 plus 4 over 2, which is equal to 8 plus 4, that is 12 over 2, which is 6. So it is 4, 6. So I found my relative max and relative minimum. Lastly, I'm going to find the f double prime to identify any points of inflection and find the intervals of concave up and concave down. So then it's easier to use this form of f prime to find the f double prime. And again, I'm going to use quotient rule. So my f double prime of x is equal to low quantity x minus 2 square times d high. Derivative of high is quantity 2x minus 4 minus high is x squared minus 4x times d low. Derivative of bottom is 2 times quantity x minus 2 to the fourth power times derivative of inner function, but derivative of inner function is just 1 over square below. I have a quantity x minus 2 squared before, so when you square that, I get quantity x minus 2 to the power 4, which is equal to, okay, now look at your numerator. Your numerator have a common factor x minus 2. So I'm going to take out common factor x minus 2. Then I have another factor of x minus 2 from the first factor and 2x minus 4 factor minus from the second term, because you took it out the x minus 2, you have a 2 times the quantity x squared minus 4x factor. Close the bracket over quantity x minus 2 to the power 4. To make this simpler, let's cancel the one factor of x minus 2 with the one factor of the x minus 2 factor in the bottom. So then now I have a quantity x minus 2 to the third power. And now I'm going to FOIL inside of a bracket and distribute the negative 2 to the second factor. So then it becomes x times 2x is 2x squared. X times negative 4 is negative 4x. Inner 2 is negative 2 times 2x, which is minus 4x. Last and last, make it positive 8. Distribute the negative 2. I get negative 2x squared. Negative 2 times negative 4x makes it positive 8x over quantity x minus 2 to the third power. So then 2x squared minus 2x squared gone. Negative 4x minus 4x is negative 8x. Negative 8x plus 8x is 0. So all I have left is positive 8 on the top over quantity x minus 2 to the third power. So let's find possible inflection point. When is my f double prime ever 0? My f double prime will be 0 if numerator will be 0. But numerator is set to be 8, so it is never 0. When does my f double prime not exist? My f double prime does not exist when x equal 2, but that's not possible inflection point either because f of 2 is not defined. So that means I have no inflection point. However, you can still test the concavity by locating 2 on the f double prime and find the sign since your graph is cut off at 2. Before 2 and after 2, your graph could behave differently. So find the test points. My test point could be 0 before 2, and I'm gonna pick 3 after the 2. So what's f double prime of 0? Plug it in right last step of your f double prime. That will be positive over quantity 0 minus 2 cube is negative number cube, which is negative. So you got positive over negative, which is negative. So this is negative, which means f is concave down from negative infinity to 2. And now test 3 into your f double prime. That's 8, which is positive, over quantity 3 minus 2 cube is positive. So it is positive from 2 to infinity, which means concave up from interval 2 to infinity. Let's now put this information of f prime and f double prime together to try to find out shape of our graph. First up, we know our graph is cuts off at x equal 2 since there is a vertical asymptote, and from negative infinity to 0, f prime is positive, so graph is increasing, but it is concave down. So you are gonna draw umbrella-shaped graph that is increasing. And we have a relative maximum at that 0. And then from 0 to 2, f prime is negative, so graph is decreasing. However, it's still concave down up to 2. So it's still umbrella shape, but graph will go down, so it will look like that. Now 2 to 4, f prime is negative, which means graph is decreasing. However, concavity is up now from 2 to infinity. So we're gonna make a cup shape that is decreasing. So graph will look like that. And then you will have a relative minimum at x equal 4. And then from 4 to infinity, f prime is positive and f double prime is positive as well. So it is still concave up, but now graph is increasing. So this is how f graph shapes looks like. So let's put all this information together to graph this original function f of x equal quantity x squared minus 2x plus 4 over quantity x minus 2. My y-intercept is 0, negative 2. I have a vertical asymptote, which is x equal 2. I have slant asymptote, which is y equal x. My relative maximum is my y-intercept, which is 0, negative 2. Relative minimum was 4, 6, which is right here. Now, we're gonna shape the graph from negative infinity to 0. I have increasing graph that is concave down and having y equal x as my asymptote, and from 0 to 2, my graph will be decreasing and it's a concave down. And 0, negative 2 is my relative maximum, so that has to be highest point of my graph. So my graph will look like that. And from 2 to 4, my graph is decreasing. And 4 to infinity, my graph is increasing, but it is concave up. So I will have a cup shape located between these two asymptotes. So on the other hand side, I will have a graph shape like this, so that I will have relative minimum at 4, 6.